Welcome to EC for 65565 introduction to microelectronic fabrication. This is lecture 26, and we are going to continue to talk about chemical vapor deposition. And specifically, we are going to discuss some different CVD systems. So last lecture, we talked about some chemical reactions, the dynamics in the CVD system. So we know the chemical gases or vapors can react on surface of solid and then produce some solid and byproduct on the surface in the form of thin films. And the byproduct are usually volatile and then will leave the surface. So here we show, you remember, so inside the chamber, we have mainstream flow with the reactants, and then we have stagnation layer and stagnant layer. I suppose there's the flow rate is 0, and then mainstream flow region. So we have the maximum flow rate. Now this we have the horizontal silicon wafer, and here the vertical silicon wafer. And so let's just work on an example. Let's see what's next size. Okay, this is APCVD. We talk about shortly. So last lecture, we have an example, but I couldn't finish. So let's work on this example. So this example 13.1. So we assume there is a gas. The gas, the composition is AB. And this AB is introduced into a reactor, a chamber for chemical vapor deposition. And suppose there is only one chemical reaction. So chemical reaction AB equals A plus B. And dual direction. And this process is run pressure is 1 atm, atmospheric pressure, or 764. And we know the temperature is 1000 K. The process is in chemical equilibrium. So we want to calculate the partial pressure for each species. PA, PB, and PAB for the partial pressure. And suppose we know the equilibrium constant K is given by 1.8 times 10 to the power 9 times e to the power 2 minus 2 electron volt over kT 4. So just solve this problem. So firstly, we can calculate K. And then K, so for T equal to 1000 K, so we can do a simple calculation. So it will be 0.154. And K is actually defined equal to, so we have pressure A, pressure B, and pressure AB. So PA, PB over PAB. So this equal to 0.54. And the overall pressure P, so is the sum of AB, PA, PB. Okay, so P is known. That is 764. So we need to find because we have 3 unknowns, we only have 2 equations. We need to find a third equation. So third equation, we can say that A, B, we have the same number. So 1 to 1. So we can expect that PA equal to PB. And then we have 3 equations and 3 unknowns, so I can calculate. So this is simple calculation. So PA equal to PB is equal to 10.54. And then PAB can also be found 739. Okay, that's a simple question. So you may come to similar homework problem or maybe in exam. Sure. Yes, good. Let's go back to the slides. Okay, so basically there are 3 different types of CVD we mentioned in last lecture. So there are APCVD, LPCVD, and PECVD. APCVD and LPCVD, that is atmospheric pressure and low pressure CVDs are thermal CVDs, and then plasma enhanced plasma CVD. So the first one we are going to discuss is APCVD. So here we show the APCVD system and reactor, basically. So inside this, inside the chamber, let's see. From top to bottom, so we have the gas source. So we have this process gas in the center, and then we have nitrogen on both sides. So this is used to work like a curtain, so to isolate this processing gas. And this process gas will flow through this shower head. And then we have these silicon wafers. On top, this is a conveyor belt. And we can load and unload the wafers. And so we have a heater to raise the temperature to 400 or maybe like 1 to 900 degrees C. Because this is a thermal process, APCVD thermal process. And then we have exhaust. So also here we have our cleaning station. So there might be dirt on their belt. So we need to have a belt cleaning station, maybe in some sort of solution. And this is the whole our basic system for APCVD. So this system is simple. And also it is fast. So in early days, this is what they used. So the pressure is high, and we know for high pressure, lambda, so the propagation length, the average propagation length, so it's very small because of the high pressure. And the transport, mass transport is slow. So this is a mass transport limited. You can see here, mass transport limited process. And it has large, high temperature, large deposition rate. So because of this large deposition rate, usually used for thick dielectric deposition. So at equilibrium, it's transport limited. The mass transfer and also boundary layer dynamics will just control or limit the process. So one main drawback of APCVD is that the quality of the deposited film is low. Potentially there are some particles. So because the pressure is high, there can be gaseous reactions in the chamber, and they generate particles. And then with these particles, you lower the quality, and also the uniformity is not good. And even the process fast. So because of this drawback, and also because it's their good thing is that it is the advantage that it's fast. So we can use silane react with oxygen to get silicon dioxide. And at a temperature about 240 to 450 degrees C. So the specific application in IC fabrication is as a so-called pre-metal dielectric. And so look at this figure. So this is a cross-section of our integral circuit. So we have transistors. So at the bottom, very small compared the metal here. And so here we have a transistor. And then we have back-end process, transistor front-end process, and we have back-end process. Back-end line, we have like metals, we have some dielectric, and we have passivation. And to deposit metal, so here we need to deposit or cover the transistor with so-called pre-metal dielectric, PMD. And this PMD is silicon, some kind of a silicon dioxide, insulating silicon dioxide or glass. So normally we introduce some phosphorus or boron. So, and we call it PSG. This is phosphosilicate glass, meaning silicon dioxide films with phosphorus. And also boron phosphosilicate glass, so BPSG. So we can use this silane. So silane is poisonous, and actually modern IC fabrication use TIAs. So that is tetra ethoxysilane, tetraethoxysilane. So there's a spelling mistake in the textbook. So, and so here we have silicon, oxygen, carbon 2, hydrogen 5. Okay, so tetra ethoxysilicon, silane. And together with ozone, so O3. So these two materials normally used for precursor, as precursor. So to provide a silicon. And of course, we can introduce phosphorus and boron to make a PSG or BPSG. So use either PSG or BPSG. And this is a little bit blue yellow. So this is pre-metal dielectric. And after this layer, so you can see here, so we have the device transistors, and on top of it, we have this BPSG layer, and then we can use reflow process to make it flatter. Okay, this is APCVD, main application in IC fabrication, used as pre-metal dielectric. And then we have low pressure CVD, LPCVD. So low pressure CVD mainly have two types. So cold wall reactor and hot wall reactor. So cold wall reactor, so we have the heated susceptor, the wafer is heated at high temperature. And the wall, the side wall, the top wall is cold, the temperature is low. So with this, it reduces the reaction rate and actually reduce deposition on the surface. And this is used for silicon epitaxial layer, epitaxial deposition of silicon we are going to discuss in next lecture. And we also have a second type, hot wall reactor. So hot wall reactor can provide a uniform temperature distribution because so we can get the temperature to be the same anywhere around the chamber. So, but the drawback is that the surface can be deposited, can be coated with this reaction product. Another good thing, and because the temperature uniform, we can expect there will be much lower convection. If we have hot region, cold region, so convection will be serious. And also, so the system must be dedicated to only one species in order to avoid contamination. And a hot wall reactor is widely used for polysilicon and dielectric deposition in IC fabrication. So for LPCVD, thermal energy is used for reaction activation. Because the system, LPCVD, works at vacuum, 0.1 to 1 pool, it's very low pressure. So the diffusivity of the reactant can be very high. So the process, the reaction rate, so the process is reaction rate limited. So also the wafers can be stacked closely. So because the temperature is uniform, so we can have uniform deposition. Normally, the temperature is controlled around 600 to 900 degrees C by using a flat temperature zone in here. So we can use several heaters to have the zone 1, zone 2, zone 3. So zone 1, so in the beginning, the low temperature, this is pretty similar to the oxidation furnace. So we have for low temperature zone and then high temperature uniform, high temperature zone and then low temperature, so and then slow down, lower down the temperature again, cool down the temperature again. Because the gas pressure is low, the gas phase reaction, which can cause particle problem in APCVD, is also low. And the contamination of the wafer and the system is low. And this is good thing for LPCVD compared to APCVD, because even though the temperature is high, but the pressure is low, the reaction is low. This is an advantage over APCVD. So we say the pressure is low, and we know mean transportation line is high. So and then lambda is high, and then so equilibrium cannot be reached, cannot be achieved. So the molecule flows and the collision will be very few. And because the process is non-equilibrium, and we have a large lambda, and the reactant is very few. So the growth rate is controlled by actually the reaction kinetics. So also because the pressure is low, and we can improve the transport, and we can minimize the boundary layer, and then we can extend the reaction control region. So for example, we can deposit polysilicon. So use high temperature to decompose silane, and then we get the silicon in solid phase, and then hydrogen in gas phase. So the temperature is about 600 degrees C, and it can be deposited with a deposition rate of 10 to 100 nanometer per minute. This can be lower than APCVD process. So for LPCVD, low pressure CVD, there's no carrier gas. So we use low pressure. There's no nitrogen there. So we just no carrier. We have no carrier gas. And because of the low pressure, low collision, there's fewer gas phase reactions, fewer particle contamination. It also eliminates boundary layer problem because we minimize the boundary layer because of low pressure. And we have low pressure, and then we can extend the reaction limit radius. So for LPCVD, we can get very good conformal growth. This is much better than sputtering or high pressure APCVD. So APCVD is more directional. Okay. We have and also the plasma CVD. So the process deposition rate depends on temperature. So we can use this temperature control with the hot wall furnace to control the deposition rate. So you can use low pressure CVD to deposit silicon and polysilicon and dielectrics. So we can also use LPCVD to deposit metal, and we call it metal CVD process. Normally we use cold wall LPCVD. So because for so this is because for in the early days we use a sputtering process to deposit metal metal contact or metal interconnection. And the problem is that, the sputtering process, the step coverage is a big problem. So in order to make a good coverage, so we need to taper the sidewall. So like here. And, if we make this sidewall, and we also can use a cap like here, and actually this we have, this takes place. This cap and the sidewall takes place. So we have less contact in a certain area. And you look at the top view, we can also see this. So it takes a lot of space. And with the device scaling further, and we have smaller contact and a smaller hole, smaller via, it can be this sputtering process can be a big problem associated with the step coverage. So we introduced LPCVD to deposit metal. So use low pressure CVD, as we mentioned, it has very good step coverage. And instead of you to make a cap contact, so use a plug. We deposit a plug, and it will decrease the surface area and have more dense metal contact. And this is shown here. So here we have this is the source, the drain, right? And we need to make a metal contact. We deposit the contact, and then we deposit the interconnect. And because it is very small, so we use LPCVD. So LPCVD, we use so tungsten. Normally we use tungsten. So here, not copper gold. So we use tungsten. So tungsten WF6. It has so the melting point is very low. So at room temperature, so it's actually a gas. Yeah. And so then we can use a crude oil LPCVD, and then tungsten WF6 and react with the H2. So I think we get tungsten metal. I think we have HF. So here is shown. We show tungsten contact plug. Yeah. So after, so we actually deposit pre-metal dielectric like silicon dioxide using APCVD, and then we pattern this PMD, and then we deposit this metal tungsten by using LPCVD method. And then we deposit actually copper. So copper actually deposited using electroplating method. So before we talk about electroplating method, let's finish CVD part. So CVD part, the third type is PECVD. So plasma enhanced CVD or similar to plasma CVD compared to thermal CVD. So plasma CVD is mainly used for dielectrics. So LPCVD or APCVD is a thermal process, meaning the process is done at a high temperature. But sometimes the inner layer of metal or inner layer of dielectrics may not be able to withstand this high temperature, meaning we cannot use that LPCVD or APCVD. So we can use plasma CVD. So for APCVD or LPCVD, we use thermal energy to activate the reaction process with high temperature. And then for plasma enhanced CVD or PECVD, we use plasma energy to activate this process at low temperature, less than 300-400 degrees C. And so this process is similar to a sparging process. So we transfer energy into the reactant gas and forming the radicals. This is the decomposition process. And in thermal CVD, we use thermal energy for this decomposition process. So PECVD is also a surface reaction limited deposition. So the substrate temperature cooling is very important to ensure uniformity. And this is a PECVD. So there are different type of geometries for PECVD. So we can have coolable parallel plate. So this is similar to your geometry, similar to your so coolable LPCVD, and then here we have the hot wall parallel plate PECVD. And the third one, this is our HDP CVD, high density plasma CVD. So high density plasma, we discussed before, there are different ways to produce high density plasma. One way is using ISP, inductively coupled plasma system. So like this one. So with the high density plasma, so we can have more electrons staying in their chamber for a longer time, and then improve the efficiency. So this table lists the main applications in IC fabrication of CVD process and the associated precursors. So mainly we deposit dielectrics, semiconductors, polysilicon, and episilicon, and then metals. So dielectrics, so we have silicon dioxide, and we have oxynitride and nitride as passivation layer or insulating layer. So for precursors, like LPCVD, PECVD, for dielectric, silicon dioxide, we have different precursors. And for we can have different precursors. We can for low pressure CVD, PECVD, LPCVD, APCVD. So for example, we remember for so silicon dioxide, and then we can use TIOS and ozone for APCVD, and also we can use TIOS for LPCVD. And for silicon nitride, we may have different reaction for PECVD, LP, and LPCVD. They can be same, they can be different. For metals, especially tungsten as the metal plug, so it's WF6, the tungsten hexafluoride, as a precursor. And we can also use the CVD to deposit semiconductor. So polysilicon, very importantly, and episilicon we're going to discuss later, next lecture. Yeah, we can use silane DCS, GCS, CRTED for semiconductor deposition. Here is a more general comparison of typical thin film deposition technology, including thermal evaporation, E-beam evaporation spotting. We compare them with this PECVD and LPCVD. So for IC fabrication, go first. So we use CVD a lot, PECVD and LPCVD. You see the film density, the film density here. Thermal evaporation or physical vapor evaporation very poor. And have LPCVD, so we get the film density accent. And also associated with this CVD process is high cost, you can see. And then PCVD, LPCVD has poor directionality. That meaning very good step coverage that is desirable in IC fabrication for especially for metal layer deposition. And the uniformity, so PVD is poor, normally poor, and then CVD is better. And for applications or materials, so we can deposit metal and dielectrics using CVD, and then PECVD, plasma CVD mainly for low temperature dielectric deposition, LPCVD for dielectrics and metals. And we haven't talked about how to deposit metal carpet. So we say we can use this sputtering to deposit. Actually, that's aluminum. This we use. We can use sputtering process, and that's physical vapor deposition. But we didn't. We haven't discussed the most important thing for today's IC technology is copper, because copper has higher conductivity or lower resistivity. So we prefer copper than aluminum. So actually, we use the electroplating method for copper deposition. So electroplating is process of depositing metal in on a conductive surface of this wafer in a solution. In this solution, like here, the solution is a caustic sulfur acid, not sulfur acid, sulfate. And so we use this solution, use the solution to deposit copper. And in this solution, we have ions, the copper ions. For example, the copper ions accept the electron. And then we will have copper atoms on top of the wafer. And here, this is the anode. The wafer connect is anode, work as an anode, and we have the cathode. So the anode is connected. Anode, we use this copper source. So this copper source will generate copper ions, and copper ions go to move to wafer, the silicon wafer, and it will accept electrons and generate the copper atom deposition on the wafer. And this here shows there a gold field. And actually, you can see we have seed and we have berry. We'll talk about them in detail next slides. And here it shows the big picture. So basically here. So after a deposition of tungsten as a plug, contact plug, and then we deposit copper interconnect. So using this electroplating method. And then between them, we have this passivation layer, the final step. We have dielectric layer for insulating, and we have edge stop layer. So, and for the dielectric, mainly we just deposit using CVD method. So here we show the structure of electroplated metal plug. So it's not that simple. Actually, it's a little bit complicated. So firstly, so we have this layer, and then we deposit adhesion layer because adhesion layer. We also have a barrier layer. We have adhesion layer and then the seed layer. So firstly, maybe we need to mention the seed layer. So to deposit our copper plug using electroplating method, we need a seed layer. So as work as a metal electrode, right? And this layer typically can be done using physical vapor deposition or chemical vapor deposition. And then, so next, so because this copper, the copper can actually diffuse to the silicon dioxide and other part. And so it will do some bad things to the device performance. So we need our barrier layer, like here, the barrier layer, the black region. So this barrier layer. And this barrier layer normally not so adhesive to the side wall of the silicon dioxide. So we need our adhesion layer. And it is also not so adhesive to copper. So we have this adhesion layer between this barrier layer and silicon dioxide, and also between this barrier layer and the copper, the seed layer, copper seed layer. And then with this, all this 1, 2, 3, 4 deposited, and then we can put into the solution, and then we can deposit the plug, the copper plug, by using electroplating method. And this figure basically shows the resistivity as function of the current density in the solution, and also as function of the bath concentration. So we can say, because resistivity is important for metal interconnect, we use copper because it has lower resistivity than aluminum. And so in order to decrease the resistivity, we can use higher current, and we can use here we can also decrease the concentration of the solution. So in this way, we can decrease the resistivity and get a better electrical performance. Yeah, I think that's chemical vapor deposition. And the next lecture, we are going to talk about a similar process to chemical vapor deposition. So maybe a variation of a chemical vapor deposition. So it's called epitaxial deposition. So we're going to discuss in next lecture. And then basically we talk about all the processes involved in IC fabrication, and then following that we'll talk about the integration of the whole process. Okay. Thank you, and I'll see you next lecture.